All right, so in these logarithm problems, many times you see this Richter scale example used because this is actual real place where logs are used. And so if you've heard of the Richter scale for measuring earthquakes, here's how they calculate it. They take how many times the actual amplitude is of the, when they measure it, the seismic trace, it's the seismic movement. It's like kind of like these waves. And so how many times this is greater than the smallest detectable one. So here when they give you the first question here, so you're putting in the how many times greater the movement or the amplitude is to the log, and then it calculates it. So it's log base 10 of that. So if you have an amplitude of 200 times greater, so that's like saying what is the log of the A over A0 actually is the 200. So that's the log of 200, which again, if you just want to use something like Desmos, I do like to demonstrate that in case you haven't used it, so that you, and so again, all I was going to do is the log of the 200 there for our problem. So if you have the log of that 200, or if you have a calculator, 2.3, I think it said round to the tenths. So that's where this 2.3 came from on the magnitude over here. And then they go on and they say how many times greater. So they're looking for the 6.8 is like my answer. And I'm trying to find this ratio of how big it is. So on this one, it's going to be the 6.8. So that would be like my base 10 to the 6.8 would equal this ratio. And then it says how many times greater than a 5.9. So then we're going to divide it by, if this were the 5.9, and I'm looking for this ratio, then that's going to be 10 to the 5.9. And so when you're just going to do that, find that ratio, how many times bigger is the actual magnitude in that situation. So again, 10 to the 6.8 divided by the 10 to the 5.9. And again, I'm just going to come over here, 10 shift 6 to the 6.8, get out of the exponent layer over to the right and divided by 10 shift 6 for the exponent 5.9. And it's like 7.94. And again, that's all it was asking for here is the 7.9 rounded to the nearest tenth. And then the last one says, suppose the magnitude of the earthquake is 150 times greater. So again, the magnitude of the earthquake is 150 times as great. And so that's my magnitude, my answer. So I've got that 150. How much greater is the magnitude of the more intense earthquake than the less intense? So you're just solving this out of that ratio, and that's going to be your number of times greater. So 10 to the 150, that's an enormous number. Suppose the amplitude of one earthquake is 150 times more. The amplitude is. So how much greater is the magnitude of the more intense earthquake? So this answer came out to that. Type an integer or decimal. Suppose the amplitude. Suppose the amplitude of one earthquake is 150 more, so the amplitudes are here. Much greater is the magnitude of the more intense. All right, wait, I don't think, that doesn't seem like I did the right thing there. I was reading it as the magnitude was 150 times as great, but this says that your amplitude is 150 times as great. So that means you're doing log, and if these ratios are, this one on top is 150 more, so then you would just be finding here your log of the 150. So even though it's 150 in magnitude more, when you do the log of 150 times, that's going to tell you that it's 2.176 for mine. So 2.176 rounded to the nearest tenth, so that'd be 2.2 times greater in magnitude. Okay, so there you go. Problem 6.5.40.